Have you ever wondered if our standard logical tools can really capture all the nuances of dependence and independence in reasoning? Yeah, the question has had philosophers scratching their heads for centuries, and it's the puzzle that we're going to try to tackle in our deep dive today.
Yeah, absolutely. And, for anyone listening who's got that philosophical mind, you're really in the perfect spot to grasp the subtleties that we're going to uncover today as we explore independence friendly logic, or IF logic for short. We've been poring over this really comprehensive entry from the Stanford Encyclopedia of Philosophy, and, it hits you right away. This isn't just another logical system. IFA
Yeah.
logic really dives into these super fundamental questions about how much we can actually express, what truth really is, and even the very bedrock of math itself. So get ready for some serious aha moments as we break down these ideas.
Couldn't have said it better myself. So our goal today is to pull out those big aha moments, those key insights from all this research on IF logic. We really want to hone in on what sets it apart from that first order logic that, is probably familiar to a lot of you. And to us, the core difference seems to be how IF logic tackles this idea of dependence and independence between quantifiers. We'll be drawing all of this from the Stanford Encyclopedia of Philosophy, so, we're talking about a super detailed philosophical encyclopedia entry, perfect for our philosophically inclined audience, right?
Right. And the heart of the matter, the thing that IF logic really grapples with, is this concept of quantifier dependence. Think about your experiences with mathematical analysis, right? Rigorous definitions of limits, continuity, derivatives, all of these hinge on understanding exactly how different quantifiers relate to each other. It's all about whether or not that there exists truly depends on all the for all conditions that come before it.
It's like that classic line, for all epsilon, there exists a delta. And that sticky point is whether delta can be, specific to the values we started with, or does it have to be universal?
Yeah.
Really gets you thinking about what we mean by general.
Exactly. Take the definition of continuity for a function. Okay. So for every point, call it A, and any teeny tiny positive epsilon, we got to be able to find a positive delta such that for all x within delta of A, the function's output stays within epsilon of FA. Now, the tricky part is, with uniform continuity, does delta have to depend on both epsilon and that specific point A? Or can it just depend on epsilon, making it uniform across all those A's?
Now this is where it gets interesting for a philosopher, someone who thinks about precision in language and logic.
Hmm.
How does IF logic actually write this distinction into its notation?
That's where that brilliant slash comes in, the independence indicator. It's IF logic's big syntax innovation. So picture this. Uniform continuity in IF logic might look like this. For all VU epsilon exists delta, for all XR. See that for all is stuck onto exists delta. It's shouting, hey, delta can depend on epsilon, but not on A. But in standard continuity, you wouldn't have that independence. It'd just be for all epsilon exists delta, reflecting that nested scope of the quantifiers.
Okay, so I'm following. In regular first-order logic, if you've got an existential quantifier nestled inside a universal one, bam, dependence implied. Like in for all x exists yrx, that y we pick could totally depend on the specific x we're looking at.
You got it. And we usually use Skolem functions to formalize this in logic. These functions give us a specific value for that existentially quantified variable based on the universally quantified ones before it. So in for all x exists y r x, the Skolem function would gobble up x and spit out the matching y.
But if logic, with that slash, changes the game entirely.
Yeah.
Exists z for y r x away z, even though z sits inside the scope of both x and y, that for all y is screaming, nope, z doesn't care about y, it only hangs out with x. It's like a direct line showing independence right in the structure.
And what's huge for us as philosophers interested in the power of language in these systems is that this little slash actually unlocks a whole new level of expression. If a logic can express relationships that standard first-order logic just can't, and one of the key results is that we can now work with finite, partially ordered quantifiers, sometimes called Henkin or branching quantifiers.
In quantifiers. It sounds like we're getting into even more complex dependencies. Can you unpack that a bit more for a philosopher who spends their time thinking about causation and influence?
Picture those situations where dependencies aren't in a neat line. Like, imagine we've got two independent choices to make, maybe X and Z. Then we have to choose Y, but it depends on X. And we have to choose W, but it depends on Z. That's branching dependence, where the choices aren't linked up in a single chain. That's what Henkin quantifiers are for. They look something like this. Pekin matrix for all z exists W and matrix RXYZ. The structure itself shows that branching.
I see it. That parallel structure signals that we're not talking about strict sequential dependence anymore. How does IF logic represent this nonlinear dependence?
The magic is that this Henkin quantifier is only true if we have functions, one that sets x based on x and another that sets w based on z, such that rxyz holds. And guess what? The IF logic sentence exists yrxyzw
Yeah.
captures that exact same truth condition. That for all x on exists makes it crystal clear. W can depend on z, but it's totally ignoring x.
Wow, that's a powerful connection. So IFS logic gains expressive power by being able to show these intricate nonlinear dependencies. The entry even mentions that this lets it express things that first-order logic just can't, like the Dedekind infinity of a domain. What does that tell us about the limits of standard logic?
So Dedekind infinity is about defining an infinite set as one that has a proper subset that's the same size. You can map the set one-to-one onto a part of itself, but not the whole thing. Standard first-order logic can't tell us for sure if a domain has this property. But IF logic, with its fancy dependence control, can. It shows that our standard logic might be missing certain kinds of infinity.
And the source highlights Hintika's idea that dealing with quantifier independence directly is the most natural way to express variable independence at the first-order level. He even uses the example of kinetic energy, which I thought was really cool.
Yeah, that's a good one. The kinetic energy of something depends on its mass and velocity, but not on the specific object itself. AFEF logic nails this. For all B, for all V exists E for all B, if B is a material body. Energy equals fracq2. That for all B on exists E is key. Energy depends on mass and velocity, but not on which specific body we're talking about. Hintika even goes so far as to say that AF logic could capture all these basic relationships of variable dependence and independence that we use when we reason about the world.
That's a bold claim. It could change how we think about the power of first-order logic. So where did this IF logic come from? The entry mentions game theoretical semantics.
Ah, yes. The roots of IF logic are in game theoretical semantics, GTS for short. Hintika developed it, and it was partly inspired by Wittgenstein's idea of language as a bunch of language games. The main idea is that the meaning of things in language, especially quantifiers, is tied to specific actions. For quantifiers, it's all about looking for and finding values in a domain.
Meaning as activity. That sounds very Wittgensteinian. How does this translate into a formal system for logic?
Okay, so in standard first-order logic, we have semantic games. They're called GIFM, and they're like a game between two players. Zero-sum, perfect information played with respect to a model M. Picture one player trying to prove a sentence false and the other trying to prove it true. With a sentence in pre-next normal form, something like for all x exists y or war x, y is zw, the game goes step by step. Player 1 picks x, then player 2 picks y, then player 1 picks z, and finally player 2 picks w. If rxyzw is true in the model, player 2 wins, otherwise player 1 wins.
When you say perfect information, you mean both players always know all the moves that have been made, right?
Exactly. And whether the sentence is true or false comes down to winning strategies. The sentence is true if player 2 can always win, no matter what player 1 does. These strategies often map to those Skolem functions we talked about. And if player 1 has a guaranteed win, then the sentence is false. Hintika even used this GTS framework to analyze how meaning works in everyday language.
Okay, so that's the game theory behind truth in first-order logic. Now, how does IF logic, with its focus on independence, bring imperfect information into these games?
This is the big change. If logic games have imperfect information. In first-order logic games, everyone sees every move. But in IF logic, those independence indicators mean that a player might not know all the moves that have been made before. It's like making decisions in the dark.
Can you give an example? Let's go back to that earlier sentence.
Let's look at for all x exists, y for all exists, y for all z exists, y for all z again. The moves are the same as in the first order version. Player 1 picks x, player 2 picks y, player 1 picks z, and player 2 picks w. Whoever makes Baris D true wins. But here's the twist. Player 2's strategy for picking W changes. The for all x means that this strategy can depend on z, but not on x. It's as if player 2 doesn't even know what x is when ticking W.
So IF logic is still about whether player 2 can always win, but now there are these extra rules from the independence indicators. What if neither player can guarantee a win under these conditions?
Then the sentence isn't true or false. We call it non-determined. This non-determinacy is a big difference from classical logic, where everything is either true or false. Hintika's point is that this game theoretical framework for IF logic, with its focus on who knows what, gives us a better way to represent dependence and independence between variables. It suggests that the meaning of our logical symbols might be more about these strategic interactions with limited information than traditional semantics have accounted for.
This is fascinating, but imperfect information and non-determined sentences sound like they could really shake things up in terms of the basic properties of logic. The entry mentions non-axiomatizability and the failure of bivalence. Can we unpack those for someone who's used to classical logic?
Of course. Let's start with non-axiomatizability. First-order logic has a complete proof procedure. That means there's a set of rules you can use to derive all the logically valid sentences. If iLogic doesn't have that, it's what we call semantically incomplete.
Why is it that this ability to deal with complex dependencies makes it impossible to have a complete proof system? What's the reason behind that?
Think about IF logic's ability to express ideas about infinity, like Dedekind infinity. We can use this power to indirectly link the validity of IF logic sentences to the truth of first-order sentences in all finite models. Now, there's a big result in logic, Trachtenbrott's theorem, which says that we can't list out all the first-order sentences that are true in every finite model. There's no computer program that could do that. But if IF logic had a complete proof system, if we could generate all its valid sentences mechanically, it would contradict Trachtenbrott's theorem. Because IF logic can deal with infinity in ways that standard logic can't, it runs into similar problems with finding all its truths.
So the same power that lets IF logic make these fine distinctions about dependence also makes it impossible to have a purely mechanical system for finding all its truths. It's a big change from the idea of a perfectly decidable logic. What about the failure of bivalence? That seems like a radical challenge to classical logic.
It is a major departure. In classical logic, every sentence is either true or false. There's no in-between. But in IF logic, we have these non-determined sentences. They pop up when neither player in the game can guarantee a win because of imperfect information. So a sentence can be neither true nor false in a given model.
And this must affect other basic logical principles, like the law of excluded middle, right?
Right. The law of excluded middle says that for any proposition P, either P is true or its negation is true. This doesn't always hold for the strong negation in IF logic when we have these non-determined sentences. In fact, a sentence is non-determined precisely when its disjunction with its strong negation is not true. It goes against a deep-seated principle of classical reasoning.
The entry also mentions something about the truth and falsity of IF logic sentences and the independence indicators. It seems like in some cases, these indicators might not actually matter that much.
That's a good point. When we're trying to figure out if an IF logic sentence is true, meaning player 2 can always win, independence indicators on universal quantifiers don't affect the result. And when we're checking if a sentence is false, meaning player 1 can always win, independence indicators on existential quantifiers don't matter either. The logic allows these structures, but they don't change whether the sentence is true or false in those specific cases.
One of the most striking claims was that IF logic, even though it only quantifies over individuals, can express the same things as existential second-order logic, or ESO. That's a pretty wild idea for a philosopher who's thinking about the hierarchy of logical systems.
It is a remarkable result, and it depends on the axiom of choice. What it means is that for every IF logic formula, there's an equivalent formula in ESO that's true in the same situations, and vice versa. ESO goes beyond first-order logic by letting us quantify over relations and functions, not just individuals. The fact that IF logic, which only deals with individuals, can do the same things raises a deep philosophical question. Could it be that the power we normally associate with quantifying over higher-order things like sets and functions can be achieved by carefully controlling the dependencies between our basic first-order quantifiers?
That's really something to think about. So things like Dedekind infinity, which are outside the scope of standard first-order logic, can be expressed both by IF logic's way of handling dependencies and by directly quantifying over functions in ESO. It makes you wonder about the supposed boundaries between different types of logic and what really makes a logic expressive.
Definitely. And it supports Hintika's view that IF logic is fundamentally a first-order logic because the games only involve choosing individuals. But this is a big debate, because some argue that the implications of IF logic, like its equivalence to ESO, push it beyond what we usually think of as first order. Being able to express things that seem to need quantification over sets or functions suggests a deeper link to higher order logic.
The entry also talks about how Tarski-type semantics and compositionality don't work for IF logic. These are basic principles for understanding meaning in logic. What does this tell us about how meaning works in IF logic?
Yeah, Tarski-type semantics defines the truth of a sentence based on the truth of its parts. Compositionality means that the meaning of a whole expression depends only on the meanings of its parts and how they're put together. In IF logic, the meaning of a quantifier, especially one with an independence indicator, seems to depend on the context. It's not fixed, but rather changes based on its relation to other quantifiers, even those outside its immediate scope. This makes it really tough to come up with a Tarski-type compositional semantics for IF logic.
But the entry does say that Hodges created a compositional semantics for IF logic, though it's not the standard Tarski type.
Exactly. Hodges showed that you can have compositionality, but you have to move away from evaluating formulas based on single variable assignments. You need to look at sets of assignments. This can capture the dependencies and independencies in IF logic, but it's not Tarski type anymore. Plus, Cameron and Hodges proved that you can't have a Tarski-type compositional semantics for IF logic. Hintika argued that compositionality, while nice, isn't strictly necessary for a logic to be useful and insightful. He says the focus should be on representing meaning accurately, whether or not it fits a compositional framework.
And then there's that crazy idea that IF logic can define its own truth predicate, something that Tarski showed was impossible for first-order logic. How does IF logic get around this?
Tarski's undefinability theorem relies on some assumptions. One is that negation is contradictory. Another is that the logic can express self-referential statements. But negation in IF logic isn't always contradictory because we have non-determined sentences. This weaker negation lets us build self-referential statements about truth without running into the same paradoxes as in first-order logic. Hintika and Sandhu even used this to challenge Tarski's conclusions about natural languages, suggesting that maybe a language can define its own truth even if it's not Tarski-type compositional.
So IF logic really opens up a lot of philosophical questions. The entry mentions its implications for the place of logic and the type hierarchy, the philosophy of set theory, and even how we think about doing math.
Right. About the type hierarchy, Hintika insists that IF logic is still first order because its games only use quantification over individuals. But others, like Pfifferman, say that what IF logic can express, like its equivalence to ESO and its ability to deal with cardinality, shows it's connected to higher-order logic. The fact that figuring out if an IF logic sentence is valid is as hard as dealing with full second-order logic further muddies the waters.
And what about set theory?
Hintika argues that standard set theory, like ZFC, doesn't really reflect how we intuitively understand truth in math, which he thinks is more about Skolem functions, a second-order idea. He sees ZFC as trying to fit the richness of math into the limited framework of first-order logic. He even says that big questions like the continuum hypothesis are actually problems in second-order logic that ZFC can't definitively answer.
That's a totally different way to think about the foundations of mathematics. It suggests that our standard framework might be missing some key parts. The entry also mentions extended IF first-order logic, or EIFL, which adds classical negation to IF logic. What does that change?
Adding classical negation to EIFL makes it even more powerful. It can now express things like finiteness, well-foundedness, and continuity, which standard IF logic can't. But it also loses some nice properties that IF logic shares with first-order logic, like compactness and the Lowenheim-Skolem property. And because of the way classical negation works, you can't define a self-applied truth predicate in EFL without running into problems. Hintika has suggested that EFL could be a way to rebuild all of math within a first-order system, essentially reducing everything to EIFL sentences and questions of validity in IF logic. But this is a pretty controversial idea.
Lastly, the entry talks about informational independence in everyday language, using the example of the villagers and townsmen.
Yeah, Hintika argued that natural languages like English have structures that show informational independence. This means that the quantifiers we use every day might be even more expressive than standard first-order logic. The example where choosing relatives might be independent across different groups of villagers and townsmen illustrates this. He even claimed that any sentence with finite, partially ordered quantifiers could be expressed in English. And if you look at questions like, who does everybody admire? And why, you see how informational independence affects things like knowledge. Even the difference between didicto and do readings of knowledge can be analyzed using the independence indicator.
So, to sum up, it seems like independence-friendly logic gives us a much richer and more expressive way to think about logic than standard first-order logic. It does this by explicitly dealing with the complex relationships of dependence and independence between quantifiers. This shift in perspective has big implications for philosophy, from math to language to logic itself.
Absolutely. And for a philosopher like yourself who's interested in these fundamental questions, it's really amazing to see that a logic that seems to stay at the first order level can actually do things we thought required second order logic. And the fact that IF logic can seemingly get around Tarski's undefinability theorem for truth is mind blowing. These are things that make us rethink some of our most basic assumptions about formal systems.
It really does. For anyone listening who's wrestling with the foundations of logic and mathematics, IF logic offers a new way to look at those age-old questions about expressiveness, truth, and what logical consequence really means. It suggests that logic might be a lot more nuanced and interconnected than we thought.
This deep dive has only scratched the surface of these ideas. We encourage you to explore game theoretical semantics, the complexities of second order logic, and the debates about the foundations of mathematics that these concepts have sparked. How might embracing logics like IF change our understanding of the limits and possibilities of formal systems for capturing the complexity of human reasoning and our understanding of the world?
A fantastic question to ponder. It really gets to the heart of philosophical inquiry. Thank you for joining us on this deep dive into the fascinating world of independence-friendly logic. We hope it's given you some new ways to think about the power of logic. We'll be back soon to dive into more thought-provoking topics.